Good morning. Hope everybody's doing okay. Today we're going to do a little bit more of what we started with yesterday in terms of selecting data. We're going to talk about how to set up data set series, so examining time series of data. We're also going to talk about derived fields and how we can create our own derived fields. And finally, we're going to go a little bit more in depth on which data objects are available and how we can utilize those data objects. Finally, if there's time toward the end, what we're going to do is we're going to talk about how we can understand the data that is loaded, as well as how we can set up and write scripts that can be used in memory conservative fashion and some of the things that YT provides for that. Okay, so we're going to go ahead and I am going to get started with a fresh notebook, but before we get any further, I want to thank you all for being here. And let you know that yesterday I didn't get the video posted immediately, but it should be posted now. Okay. All right. So let's go ahead and take a look at our notebook. I'm going to be starting up day 2, notebook 1. Oops. So yesterday we saw a couple things that were of interest. We went over how to load up and inspect some grid data, how to do the same thing with particle-based data, and how we can analyze the data there in a particle-centric way, particularly with SPH particles. And then toward the end, we talked about a couple different sets of, or a couple different ways of looking at the data in terms of visualizations. We're going to return to that, and we are going to utilize one of the data sets that we had talked about before. So I'm going to import YT, and I am also going to import widgets. And again, widgets is, and I am in the Conda environment that we set up yesterday. Widgets is the package that YT that is developed in YT that provides a couple different GUIs for quick analysis of data. And then just because, oh goodness gracious. Oh my goodness. Yeah, I think that I made a small mistake earlier when I was setting up my system. So this is not something that you should ever have to see. I was doing a little bit of development overnight, and that kind of put us in a spot. So we're going to talk about a couple things, and we're going to start with our Galaxy dataset again. And what we're going to do with the Galaxy dataset, should be just about done. We are going to load our isolated Galaxy dataset. Now, yesterday I kind of skipped over some of this, but there are several different fundamental ways of visualizing data in YT, and we saw most of them. The first one that is usually the first thing that people do is a slice plot. And a slice plot takes an infinitesimally thin slice through the domain and then shows you the values at each point in that slice. For finite volume codes and grid codes and whatnot, that will be piecewise constant. For codes that are based on closure functions like smooth particle hydrodynamics, it will compute that closure function at each of the individual points. And same thing for finite element. It will compute the value at each individual pixel. I showed how to do that using the R operator, but we can also do that using the slice plot function. So the slice plot function takes as its first argument the data set, and its second argument either an axis, like x, y, or z, or a vector that describes the normal to the plane that you want. So you can either align it with an axis or you can align it arbitrarily. And we briefly saw that with how we could do that with angular momentum vectors yesterday. But here, we'll just align it with the z-axis. And then you can specify the field that you want. So I know I talked yesterday about fields. Specifically, I talked about how we can specify field tuples. So how you can specify the field type and the field name, such as gas, density. For cases where fields are ambiguous, that is required. For cases where the fields are not ambiguous, so for instance, if there is only a gas density field, we can do it like this. If you're in a Jupyter notebook, you can then either display P or using something like display P, or you can just type P and have it go, and you can also do p.show. And so here we have our slice plot, and yesterday we talked about how to zoom. You can also set the width to be something physical. You can set the origin in order to have it display. Here the origin is set at the center of the plot. You can set the units on the axes as well as here. And one thing that I should note is that the units are checked. So if I set the units for my density field to be something that is inappropriate, such as centimeters per second, it will actually tell me that there is a unit conversion error, that it cannot be converted between those. And not only does it tell me that, but it tells me cannot convert because it's a dimension of mass over length cubed, and I'm asking for it in a dimension of length over time. So it will check for you and help you out with that. We saw a couple of the annotations, but there are other annotations that we can do. So one example of this, let's annotate scale. So we can say corner lower right. Sure, let's just use all of our default objects here. And you'll see down here 100 kiloparsecs is annotated. And if we zoom in, because this is conducted at the YT level rather than at the matplotlib level, when we conduct a zoom operation, it's aware of the change. Now, mind you, there are some shortcomings to this. If we zoom in 5 again, you'll see that it still says 100 kiloparsecs. So if we want to fix that, we can clear annotations, and then we can add a new annotation to it. So while the length remains the same, it won't automatically scale to fit within the view. Another common annotation that we might want to do is we can annotate based on velocity. Velocity accepts a factor. By default, it sets it to 16, which is the number of zones that it will skip in between. So if we just do annotate velocity, then every 16 pixels, an arrow will be set. So you can see that now all of our arrows and their bases are at the pixel centers, point in the individual direction of the local velocity. And if we zoom out by a factor of 0.5, see that it still continues to follow the correct item. There's one thing that is common amongst most of our annotations, and that's that you can pass keyword arguments to matplotlib. So as an example, here it says plotargs allows you to pass in matplotlib arguments. See matplotlib axes.quiver for more information. So let's go here, and let's say that I want my arrow to be white. I go matplotlib.axes_quiver, and I look here, and I see that one option I can supply is I can supply face color. So let's go here, and we will annotate velocity, and I will say plotargs equals face color white. Oh, I guess I don't need to do that. I can just pass them in, but I will leave it like this for now. So you see, now all of my arrows are white because I've passed that argument through YT into matplotlib. I can clear my annotations again. There are a number of different annotations you can do. Some of them are really fun, like line integral convolution. I'm not going to show that one, but there are other ones such as annotate grids that allow you to overlay specific information about the data set. So here we can see where the individual grids are. We can even annotate cell edges if you're really in the mood for a busy plot. You can see there, you can't really see anything in the data set anymore because it's overlaying all of our cell edges. The main advantage to this is that if you're doing something that that requires interactive exploration, applying these annotations is done in data space and is done with respect to the underlying data objects, and that allows you to move about in data space. So, for instance, if I were to want to set my width to be something, I could set it to 10 megaparsecs. I probably shouldn't do that though because it's much larger than the simulation. And any of my annotations are set within that data space. Okay. So let's talk about how we can link some information here. So let's take a look at what we had talked about yesterday, which was how to get the full data set. So we talked about data selectors in terms of spheres, disks, regions, and so on. There's also a special case, which is the all data object. That gives you every piece of data in the simulation that is not covered by something that is higher resolution. So for particle data sets, that just means all of the particles. For grid-based data sets where you may have overlapping grids, the higher resolution grids are considered to be, oh, excuse me, no Mandalorian this morning, so I don't know why I'm so, oh, wow. Somebody wants to offer promotion of my channel. That's exciting. Let me go ahead and I'll definitely, yeah, get on that one. Okay. We can take all data, and that gives us a region there. And we talked about how you could do 1, 2, and 3-dimensional profiles. Let's see. All right. And we can do that using the profile command. And you might remember that the profile command accepts our axes along which we want to bin and the fields that we want to bin. So, as an example, let's bin along the density and temperature. And let's take mass as the field we want to accumulate. And we just want to accumulate it, so we don't want an average. And so we say weight field equals none, and then we plot it. So this is our mass distribution as a function of density and temperature. And by default, I want to say it goes to 64 bins, but we can actually change that. I think it's bins equals 128. Maybe it's n bins. Yeah, n bins equals 128, and you'll see now it's, about twice as fine. But at the end of the day yesterday, I alluded to the fact that we can also do cut regions. And there are a couple shorthands for cut regions, but you can have what's called a cut region on any data object. And what this does is it evaluates, it can receive functions to evaluate what the field values are, and then either remove or include them based on their characteristics. But one of the most common reasons that people use this is they want to exclude below a certain value or include above a certain value or things like that. So let's take a look at exclude above. So with exclude above, you can say field, value, and optionally the units. So if I do dd exclude above, and I want to exclude the temperature above a value of, let's say, 20,000 Kelvin, I can say dd.exclude above temperature 20,000 Kelvin. And let's call this cool gas. Now, if I profile cool gas, and actually I can see this if I do .extrema temperature. Oh, quantities.extrema temperature. You'll see that it only ever goes up to 19,098. But let's take a look at that more carefully. So cool gas dot profile. Let's bin it again by density, temperature, n bins equals 128, weight field equals none, and plot it. You see now, none of the data that is above 10,000 Kelvin or 20,000 Kelvin is included, and it sets the limits appropriately as a result of that. Let me take a step back and show you one of the other fundamental operations and fundamental visualizations in YT, and that's the projection plot. Projections integrate or accumulate along some axis. In general, projections accumulate along one of the three Cartesian axes, x, y, or z, but they can also receive arbitrary values, normal vectors that they can accumulate along. They don't necessarily, that's weird. They don't have to accumulate just by summing or by integrating. They can also accumulate by computing the min or the max, and they can also sum up as well. But in typical cases, what we do is we conduct a line integral along an axis, where we multiply the path length by the field value, and then we sum up along that. So, for instance, we might take a projection plot of density, and we can show it. And you'll see here again, it's grams per centimeter squared. However, we can also conduct operations in order to compute the average. So here, we can take the weight field is equal to the density. And now, rather than computing the column density, it computes the average density. So this is the density-weighted average density along the line of sight. And if we zoom in, we can see this is the average density, and that gives us an idea of the characteristic value of density along our line of sight. Much like profiles, these can also accept data objects as sources. So we can say yt.projectionPlot ds for our data set along the z-axis. Let's get the density with a weight field of density. And we can say data source is equal to cool gas. And in this case, we have only the cool gas showing up. If we zoom in a little bit more, I think it'll be more clear. You can see that we've cut out some areas. And so it doesn't look exactly the same. And in fact, there are artifacts because we've applied a hard cutoff inside our simulation. We can do the same thing by excluding below. This time, let's exclude below, and let's say 5,000 Kelvin. And let's take our our projection plot. And this time, let's just do column density. So this is just our hot gas. See, we have a very different situation. The structure is still very similar, but I suppose really we should be excluding below 10,000. So let's try that instead. There we go. Now you can see it's mostly the halo here. None of the background IGM is there because the background IGM is just initialized to a placeholder value in the simulation. Now, mind you, one of the things that we can actually take a different look at with this is here we can also bin it based on the density and the velocity magnitude. And because we're no longer binning along one of the fields that we've used as an exclusion, we would expect to look a little bit differently. So here's density and here's our velocity magnitude, whereas were we to do this with our full data set, see that it looks different. We have a bunch of low density hot gas, or cool gas. Okay. Yesterday, we talked about the region object. And I also did a couple different NumPy-like operations on our data objects. This morning I showed you the projection plot and the slice plot operations, but both of those are accessible right off of our hot gas object or our cool gas object. So for hot gas, if we wanted to take the mean density value we could take the mean density value as weighted by density along the x-axis. Oh, it's just weight. And here you can see there's our mean density value along the x-axis according to weight for our hot gas. And this is just our input data source. And if we were to zoom in, we would see the same shape that we saw up above. We can also integrate density along an axis. And this is the projection plot that is unweighted. So in order to compute a projection plot, we can think of it as integrating if it's unweighted. And if it is weighted, we can think of it as taking the mean along an axis. There are other operations that we can do. So let's say dd equals ds dot all data. We'll create that again. We can compute the min of a given value, but we can also compute argmin. And that tells us the specific location. And this is a function that's available in NumPy, so if we import NumPy as np, np.random.random, we could do np.argmin a, and it tells us the position at which a is minimized. We can do the same thing with dd, so argmin density tells us the xyz position, but we can also specify the axis. So we could say argmin of density and give me the temperature. So that will tell me the temperature at the minimum density location. The next thing that we can do is we can say one second, let me pause. Okay, back. We can compute multiple fields sampled along this as well. So if we take the argmin or the argmax of density for temperature and density, we can return both the minimum density, which, let's make sure, yeah, it's identical. Whew, good. We can return both the temperature and the density at that minimum location. And this can be any of our fields. There are also a number of different physics fields that we can do. So you'll note that here, a couple of these are replicated in the NumPy-like fields that we saw. But if we do dd.quantities, where dd is really any data object, it could be our sphere, it could be our hot gas, dot quantities, we have an angular momentum vector, a bulk velocity, which is the mass-weighted average velocity, the center of mass, which is the mass-weighted position average, extrema, so if we were to do extrema of velocity x, it gives us our minimum and our maximum. There's also spin parameter, total mass, total quantity, weighted average quantity, and weighted standard deviation. So if we wanted the total quantity, let's say that we wanted to know the sum of the momentum x. This would return to us the total momentum along the x direction. There's a shorthand here for total mass, where what it does is if there are particles inside a grid simulation, it will return to us both the total mass in cell values as well as the total mass in particles. Now, if we're doing that for a cut region like we've done here, it actually takes a fair bit longer because it has to figure out which cells include which particles. So I'm going to quick cancel that and just do it in dd. Let's rerun everything. Okay. So the next thing we're going to do, now that we've seen how to do advanced data object selection, we've seen how to do plots from a couple different perspectives, we're going to talk about time series data. So one very common thing that happens is you will have multiple different data sets at different times inside a simulation, and you may want to examine them. Let me let my notebook propagate. I'm going to create a new notebook while it goes. Okay. We're going to import YT. We'll import widgets as well, just in case. And this time, instead of using load sample, we're going to use load. So the load, there are multiple different load commands in YT. See, there are things like load AMR grids, load HDF5 file, load hexahedral mesh, octree, particles, sample, which we've used a lot, load uniform grid, load unstructured mesh. We're going to say load, and I'm going to say Enzo Tiny Cosmology, DD, here's hoping that I have that in my file system. I'm actually not sure that I do, but we'll check in just a moment. Excuse me. Okay, so we're now going to load these, and we now have the ability to iterate over our data set. So you'll see that I've used question marks here. These question marks refer to the file system selection operations. In this case, DD question mark means allowing any values to take those characteristics. And we're going to look at this, and we're going to say ds.current redshift. You'll see it's loaded them all up, and now we can iterate over them. And as we do that, it will load each one individually and print out for us our values. So let's do this a little bit differently. We will say redshifts equals that. And now redshifts.append string of the ds, we'll do a tuple string of ds and ds.current redshift. Now you can disable the logging. I'm going to do that, but in general, I don't like doing it. And so now you see here we have DD0049, and you can see it goes all the way down here until we get to what amounts to redshift 0. These are in order in this particular case, but in some cases they may not be. So, what can we do with this? Well, let's come up with our Extrema dictionary. Extrema list. So for each data set, we'll set z is equal to ds.current redshift. T is equal to ds.current time.in units gigayear. And now let's come up with, let's say we want to find out our density and temperature extrema. So we'll say ds.allData. We'll assign that to a temporary variable, dd. And we'll say dd.quantities.extrema. And we'll call that for density and temperature. We'll say row extrema, temperature extrema is equal to dd.quantities.extrema for density and temperature. And now we'll append to extrema a tuple of z, t, row x, temp x. And now if we look at extrema, we'll look at the first value in extrema. you'll see that it actually does have to read every single data file in this situation. Okay. So you'll see here we've got our redshift, our time in gigayears, and our extrema of density, and our extrema of temperature. So what can we do with this? Well, the most obvious thing to do is make a plot of it. So we'll import plots, say fig x is equal to plt.subplots. Now let's plot our time values. So let's see. Oh, numpy is not defined. So we're going to take np.array of the times we'll get redshifts is equal to that. Times is np array and now we'll unroll our density minimum and density maximum as well. And so let's plot. We'll set our plot to times. We'll say row min. We'll say minimum density. Row max. And actually, we'll put labels on the x and y axes, so we don't need that. And we'll say x.set x label y label and then I think we can estimate our limits. And let's add a legend. And so here, oh, I think this, does that need an R? Huh, well, anyhow, that doesn't look that great, but the math text. So here's our time since the beginning. You'll see here we have very small difference between the minimum and the maximum. And then as we move over here, it gets higher and higher. And actually, why don't we, we'll restrict it a little bit. We'll 10 to the minus 23. Oh, now it's overlapping a little bit with our legend. There we go. So now our legend is down here. We've got all this nice empty white space. So let's talk about one more data object that might be of interest before we break. We're going to talk about the ray object. And for the ray object, we're going to do I should mention that it's pretty straightforward to do other time series operations here. So for instance, for ds and ts, ds.r integrate density along the x-axis, .plot, .save. And you'll note that now, even though it's outputting all of these different things, we'll see them here in the notebook, but you'll also notice that they're being saved to the disk as well. So this is the kind of thing that in general we would want to do in our in a scripting interface rather than in the notebook interface. There are ways to turn off YT's interactive mode so that it doesn't output these things. But in general, it makes a lot more sense to do this from a scripting perspective. And you know what? Let's do an example of how we might do something a little bit more complex with this. Let me clear the output there. Oh, it's still not done. Should be done really soon. Only 6 more to go. Okay. So once we have a plot like this, let's do integrate density, axis equals x. We'll call this .plot. One of the things we saw that you could have annotations, including annotations of markers and so on. Excuse me. One thing that we can do is we can have annotations of markers that accept x, y, z coordinates. So let's take our ds.r and let's take argmax of density. And that will be our position. We'll now annotate our argmax of position. And you see there, we've got an x that shows our argmax. We can also have our text annotation. We can have our coordinate system. So in principle, you can annotate text inside the data coordinate system offset by some amount that gives you the position. So over the course of our iteration, we can annotate here and then have annotations up here describing the maximum density along with its position. So we're going to take a moment to look at how we might do that inside a script. I'm going to delete my PNGs. Now I typically use VI, or well, Vim really, or I suppose actually NeoVim. But we're going to do this inside Visual Studio Code. And I'm going to say new, and this will be our projection annotation.py. I'm going to switch my Conda environment to be the current one. And one of the neat things about some of the improvements that have been made to YT recently has been that we are now adding type annotations. And this is in large part due to Clement, and I guess Corentin did some initial work on this a while ago as well. But we're adding type annotations, which allows us to, inside the editors like Visual Studio Code, provide a little bit more help. So let's go ahead and copy our instantiation here. We're going to say TS for time series is equal to that. Now for data set in time series, we're going to say ds.r argmax density. We're going to ds.r integrate density along the x-axis. Plot that. And we'll call this px. We'll also do py. And we'll skip z for now. We'll say p.x or p_x annotate marker pos, py annotate marker pos, px save, py save. And now I'm just going to let it run. While that's going, we're going to go back to a data set that we saw earlier. And we're going to talk about the ray object. And then we're going to take a short break. So we talked about we're going to talk about two different things. We're going to talk about the ray object, and we're going to talk about point queries. So, hold on. Actually, let's take our break right now. We'll take a break for just about 3 minutes, and then we will return. So, talk to you in just a moment. Okay, welcome back. Um, Thanks for sticking with me. I am going to, uh, let's go back over to our coding interface. All right, so while we were gone, this ran, and it showed me, or it output all these different plots. And one thing I want to point out is that the naming scheme on these can be somewhat annoying at times. So I'm going to separate them into different directories. Let's do X and Y. And we can look at these. Oh, let's get rid of that histogram. You can see the X position here. It changes a little bit, like it switches back and forth between a couple of these where, maybe there's dark matter halo mergers or something like that. Anyway, minor differences in the position and the location. But you can see that if we look at it there in the X, and then here in the Y, it is actually tracking it. So despite the fact that it's a two-dimensional plot and we're supplying a three-dimensional center for the position, it knows which X and Y coordinates to yank out and put into the image plane. The other thing that I want to point out is that we can save these to directories as well. So here, if we do that and then we rerun it, you'll see that it names them the same, but we've prefixed a directory name to them. So that's an easy way to prefix our items and separate them out into different areas. Okay. The last thing before we move on, let's see, I don't think I installed but if we have MPI for Pi installed, and we're working on having different parallel backends, but for now, MPI for Pi is our principal one. If we have MPI for Pi installed, we can, instead of using for DS and TS, we can call at the top enable parallelism, and we can say ts.piter for parallel iteration. It continues to scold me about updating to a newer version of Conda. I recommend that you do this, but in my particular situation, there are some barriers to doing that. So we can now do npi run, and let's do it on 8. Here, I'll rehash to make sure I'm getting the right one. And remember, we've only changed two things, ts.piter and yt.enable parallelism. And let's remove all of our existing plots. And now you'll see that these fill up pretty fast, because now it's dispatching one to each of our 8 processors that we've allocated for the task. There are some other more fine-grained things that we can do to control the parallelism. For instance, you can have it set up into subtasks. So if you've got a big data, if you've got very large data sets, you could launch on 1,000 cores and say that you want 32 devoted to each, or 1,000 tasks, and devote 32 to each of the individual data sets and so on, and it would manage it that way. Okay, so we've seen a bunch of different data selections, spheres, slices, projections, regions, and so on. We're going to talk about how we can do line queries. So let's do, I'm trying to think what the best example here is, but we're going to load a, you know what, why don't we load a Flash data set? Let's load our old favorite, gas sloshing. So gas sloshing, if we take a quick look at it, it's pretty straightforward. It's just gas. Now let's see what happens if we take our the mean of temperature along the x-axis. See, we do get some turbulence and so on in there. Let's assign that to a plot, and then we'll zoom in by a factor of 5. Yeah, we get some interesting stuff in there. So let's examine our ray object. So the ray object, like all data objects, hangs off of the data set, and it accepts a start point and an end point. I'm interested in querying along the center of the domain to the edge of the domain. So if I want to do that, I can compute the domain center as my start point. And I just want to go to, you know what, let's do center of the domain to this point in the domain. So we'll go, our start point is the domain center, and our end point is the domain left edge. So we say our start point and our end point. And we'll say my ray is equal to that. Now this is a data object just like others. So we can say myRay.max density, and it computes that for us. It's not quite feasible to do projections because it's one-dimensional. But we can also compute things like the density at every point along the ray. We can also look at what the x values are of all the cells that it passes through. The funny thing about that is, because this is an adaptive mesh refinement data set, those x values aren't necessarily going to be monotonic. Same thing for y and z, because it uses the cell centers, not the cell intersection points. But let's take a look at what the density values are. Oh, I don't want x scale log, I want y scale log. There we go. So you can see we passed through a number of different things. So along the x-axis here, we have just the index into our array. So YT provides a couple different things here. Ray objects are special in the sense that they provide you with two pieces of information that are otherwise not available. They provide you with the t value. The t value is the parameter value at which the cell, or the parameter value at the center of every cell. Or is it the start? Maybe the start. I'll look it up. It also provides you with the dt value. I'm sorry, dt's. By construction, the sum of the dt's will always be 1. So the parameter starts at the start point, ends at the end point, and always goes from 0 to 1. So here, we're plotting this, but we can also plot and let's do semi-log y, myRay t, myRay density. And so now this shows us our query along our array, along the parameter. So now we can do stuff. Remember, we've got our p object. Let's p set width 1 unitary. We can annotate array object. So if we set annotate ray and we specify myRay, we get a line overplotted showing the position of the ray that we were querying. This also works with SPH datasets. What was it that we called our, or what was the sample dataset that we did? Gadget Disk Galaxy. Let's find our maximum density location. Let's say, actually I should have assigned this densmax equals that. Temp max is ds.r, argmax, temperature. And We've got dense max, temp max. So let's do array. And actually, those are reasonably close to each other, so that might, you know what, let's do density max to density min. There we go. Those are pretty far apart. So let's do array now, from dens max to dens min. And we can look at the density. We can see DTs. You'll note that here it doesn't quite work the same way. With SPH particles, the T's aren't normalized quite the same because of the way that we manage the impact parameter. But we can now do plot. Let me check this. Seems like it's not sorting it. Let me sort this real quick. Sorted sorted args equals np.argsort myray t. So now let's plot semi-log y myray t sorted args myray density sorted args. There we go. Yeah, there's something a little bit funny about that I'm not totally understanding. I suspect it's in the documentation and I need to refresh my memory. So that's a little embarrassing. But you can see this is our density query for our particles. And if we put them all in order, that's how it looks. I suspect what's happening is there are a couple really big particles that it's interacting with, like here at the very start, and it's popping in and out of that. And the final sort isn't getting applied. I'll look into that and update. But now we can do ds.r. We'll integrate density along the x-axis, plot that, and then p annotate ray, my ray. I have to specify that I'm plotting density on these. And there it is. There's the ray that we've integrated along. And we've got our plot that is associated with it. So one thing that is of particular interest in many of these cases is examining our data as though it were a fixed resolution grid. So there are two different ways that we can do this. We can do this in either one dimension, or in 2 dimensions, or in 3 dimensions. And the easiest way to generate a grid that covers an entire region is to use the R operator on the data set. For an SPH simulation like this, we can specify along each axis inside our region expression a start position, an end position, and a number of steps. NumPy, or Python as a whole, utilizes complex numbers using J. So 1j is a complex number, and in fact it's equal to what we would think of as I. If we multiply 1j times 1j, you'll see we get minus 1 plus 0j, so minus 1. But that's a shorthand that we can use inside our region operator. If we specify a complex step, then it tells us how many cells to discretize into. So if I do colon 128j, that means discretize it into 128 zones in that direction. If I do this in 2 dimensions, and I specify a value for the third one, and here let's do 32,000, I get what's called a fixed resolution buffer. This is a 2-dimensional object that is what is used in the back end to generate things like slices. So if I were to do PLT IM show FRB of density, I guess I forget how to. Well, anyway, let's just do np.log10 on this. See here, we've got our data set, and this gives us a 2-dimensional array that comes out of it. You can almost make out what it is, but note that the origin here is up here because of the way that image coordinates work. So if we specify origin equals lower, it might look a little bit better, and you'll see, yeah, that kind of looks like that. You can sort of see where they're coming from. But in this case, it's discretizing it into 128 zones along the x, 128 in the y, along the entire domain at coordinate 32,000. So instead, let's say that we want this to be from about, you know what? Let's go real deep. Let's do 14 megaparsecs to 16 megaparsecs along the x, or along the x and the y. So 14 megaparsecs to 16 megaparsecs along the x, 14 megaparsecs to 16 megaparsecs along the y, and still have our 32,000 as our z coordinate. You see now, looks a lot better. I guess 16 megaparsecs, yeah, we're still going to cut off a bunch here. Oh, plus this is a slice along the x-axis. Let's go to the z-axis. Yeah, we actually probably want to go, let's do 13 to 14 and 16 to 17. So 13 to 14 and 16 to 17. Let's just do 16 to 17 along those. Well, I'm having a hard time getting my exact positions correct, so. And everything seems to be coming out up here, so we'll just move on from that. We now can also do a deposition of our particles. So if we want to do this along 3 dimensions, we could do colon, colon, 128J, colon, colon, 128J, and colon, colon, 128J. And we can interpolate our SPH field onto all of these cells. Now keep in mind that our SPH field here doesn't have a lot of values in it just because of how it's defined, but we can see that it does in fact have some. So we now do fixed grid, density, sum, axis equals 0. We can see that, yeah, this is what happens when you interpolate onto a fixed grid and then collapse it along a dimension. There are a couple of reasons you might want to do this. One of them is so that you can export this to another visualization tool. Another one is so that you can export it to something like a FITS file, although we do also have FITS here. So if we do frb.density to FITS, let's see, there's our image. Oh, I guess it's to AstroPy, and then you can use AstroPy to get out there. But I think we've got frb.to FITS data. This probably requires a field. Oh, I don't have AstroPy in this environment. I did just install the environment yesterday. But you can export it to FITS data and then load that FITS data into something like DS9 if you really want. Okay. Let me consult my notes. Okay. So, the next thing we're going to talk about is derived fields. And for this, we're going to return to one of our previous data sets. We're going to return to gas sloshing. And we didn't actually see what gas sloshing looks like, so we'll take a look at what that looks like. We can do dsv equals widgets dataset viewer, and we specify our dataset. Oh, you know what? It gets really confused because of the values being in CGS. You can see that we have all these different gas fields, things like Jeans mass, KT, kinetic energy density, and so on. But what happens if we want to have a field of our own design? What we can do is we can define a function. So for instance, we'll call this function dinosaurs. And that function has to receive two arguments. It receives a field definition, and it receives a data object. The first one is typically not used except in special cases. But the second one is used in all cases. So let's say that we have a derived field, and let's say that we know that dinosaurs correspond to the temperature times the velocity magnitude. We can specify that our return value is equal to the gas temperature times the gas velocity magnitude, and then we can return it. Note here that we're defining this in a functional form. It doesn't get evaluated until it is requested. So what that means is that once we've defined this, if we tell yt that it is accessible as a function, however yt decides to chunk the fields, whether that's in grid by grid or one gigantic set of arrays, it will do so. We now apply the yt.derived field decorator. Decorators are not always well liked, but the whole point behind decorators is that what we can do is we can apply a function to a function, basically. Here we're applying the derived field function to it, which specifies that the following function definition, so this def dinosaurs, is in fact a derived field. There are a couple things that we need to specify in here. We need to specify what is the name of the field. We'll call this field dinosaurs. And in fact, let's call it gas dinosaurs. We can specify the units. In this case, it's Kelvin times centimeters per second. And we can specify the sampling type. There aren't very many sampling types, but in this case, our sampling type is cell. It's really important to note that this has to be defined before any fields are loaded. So I've defined my derived field, or before any data sets are loaded. I've defined my derived field here. Now I load my data set. And if I look at derived field list, and I scroll down, I'll see that I have a gas dinosaurs field. And if I do dd equals ds.r, and I find the max of dinosaurs, I get 6.69 times 10 to the 15, well, 6.7 times 10 to the 15 Kelvin centimeters per second. That should be so let's take a look at argmax of dinosaurs. ds.r of position gives us a single point, so we can do a point query. Let's get our velocity magnitude. And our density. And if we multiply those two, and we ask for it to be in units of k times cm per second, temperature. we get the exact same value back. So what it does is it evaluates the function inside each item, and then it treats it identically to if it had found YT had defined that function inside one of its plugin files, or if it had been existent on disk. As some examples of things that people use derived fields for, I've used derived fields to compute things like the molecular hydrogen dissociation timescale. So for instance, what I did was I constructed a complex set of derived fields that computed the interpolated formation and destruction rates for molecular hydrogen, and then I figured out what the characteristic timescale was, and then I could use that to identify instabilities in collapsing protostars or protostellar regions. So you can use derived fields in a lot of different ways. One particularly cool thing about them, and you can find more information about this in the documentation, is that you can define them in a plugin file that exists in your home directory and that gets loaded every time you load up YT. The other thing that we can do with this, and you'll see that I did this right here. I had a position and a position. Actually, I can't remember. Are we able to... Yeah, oh yeah, I forgot about this. You can have arrays that do... you can have arrays that are defined by one three-dimensional position to another, and you can specify them inside ds.r. I forgot how cool ds.r is. But we could have ray is equal to position plus, halfway out to the domain edge, or the domain center, something like that. Okay. The last thing I want to show is let's talk about field parameters. Let me see. I want to be careful about this. In many cases, field parameters are set automatically. In some cases, they are not. So let's take a look at inside our earlier, or inside a data set that includes a star formation region. So this is a data set. I want to say this was created by John Wise, but I'll have to check. POP3 Mini. So let's take a look at what this looks like. See, there's a lot of levels. There's 20 levels of refinement. In fact, widgets can't handle that fine of detail, but that's not totally true, actually. Why don't we try? I'll show you something that widgets can do. So one thing we can do with widgets is we can also have real fast plotting here. So I'm going to log the color map here. So widgets also can pass reduced data sets to the browser for interactive panning and zooming. You can't do a ton of stuff with it right now. We're working on integrating with other systems in order to make it more accessible to that. But you can do real fast panning and zooming of some things. And in this particular case, because there's a fair bit of dynamic range, it can be a little bit tricky to manage the upper and lower colors. So if we modify the lower color here, you see we can, yeah, it's, there we go. But we can see this is a star forming region. There's deeply nested area. And if we take a look at, for instance, a profile of a sphere centered on the max with a radius of, let's see, the full domain is, what is that? That's 21 kiloparsecs, 21 and a half kiloparsecs. So let's take a look at the a sphere with a radius of about 1 kpc. Let's take a look at a profile, and we'll bin this along radius and radial velocity with a field of mass, the weight field of none, so we get the distribution. You see, there's quite a lot of radial velocity going on here, particularly at the outside levels. If we drop this down, if we drop this down to radial velocity with weight field of mass, we should see a little bit smoother of a plot. And I'm actually going to make this a bit bigger. I'm going to make it let's see, it goes out to 21 kiloparsecs, so let's do 5 kiloparsecs. Let's set our radius equal to parsecs. Radial velocity I want in kilometers per second. And mass I want in msun. Yeah. We're getting reasonable values here. So one thing that we want to note is that there are field parameters that can be associated with this. So if we take our sphere and we compute our bulk velocity, that gives us the overall velocity of this sphere object. So I computed the sphere bulk velocity. I'm going to clear the data from our sphere, and I am now going to set the field parameter bulk velocity equal to our bulk velocity. So we'll do this first. We'll say SP equals ds.sphere. We'll center it on max, so we get a totally clear sphere, and we'll do 5 kiloparsecs. We'll do RV1 is equal to sp.quantities.extrema of radial velocity. And now here we'll do RV2 is equal to sp.quantities.extrema radial velocity as well. So the difference between these two is that here we don't specify a bulk velocity, and here we not only compute the bulk velocity, but we specify it as a parameter. You can see now that our extrema of radial velocity are slightly different. Now let's take a look at how that looks here. What the difference looks like in our visualization. Let's create a new window for this. Create a new view for this one too. You can see that they're very similar, but they're not identical. And in fact, there's a little bit more structure here, or there's a little bit more compression in the structure here because of the particular way that it sets the min and the max. So overall, this particular case doesn't have a major difference, but it's also not the best use case for this. There are a number of different field parameters that you can set. There aren't that many, actually, now that I know I said there are a number of, but there aren't that many. A couple of the key ones are things like the normal vector for computing things like axial velocity, as well as the center and the bulk velocity. So let's see if we can come up with a little bit more of an advanced plot on this. You know what, maybe we need a bigger data set here. All right, so I've got a deeply nested zoom. Let's integrate density along the x-axis and plot it. This is a much bigger data set. It's going to just take a second to generate. See there, we've got it. Let's set it to the center. You know what? Let's do center equals ds.r.argmax density. Remember we talked about argmax. You know what? Let's just zoom in, factor of 10. Okay, so we can see there's our object. We want to set it to our y and z, so that's center 1, center 2. There we go. Now if we zoom way in, we can start to see this little object here. Okay, so we've got this little object here. Let's compute some, oh, and you know what? Let's set our origin to window. There we go. This looks a lot nicer. Now we've got our parsecs. So let's figure out what our distribution of values looks like. And if we remember, we have a number of different fields here. So for instance, things like cylindrical radius, cylindrical theta, cylindrical z. And you'll see that these have field parameters computed in them, things like the normal vector. So for cylindrical value, or for cylindrical coordinates, we really just need the normal. So let's compute the normal. We'll say sphere is equal to ds.sphere centered at our max value, and let's give it a radius of about a parsec. Let's say 5 parsecs. And we'll say our normal is equal to sp.quantities.angular momentum vector. Now let's get a sphere that's a lot bigger. Center it at max. We'll say half a kiloparsec. Let's set our field parameter. Normal to normal. And now let's take a profile as a function of cylindrical radius. What is the average, or as a function of cylindrical radius and cylindrical z, let's find the mass distribution. You can see here the mass distribution is a function of the cylindrical radius z, as a function of the cylindrical radius. And this is because of the way the xyz coordinates work. But you see here we've got our cylindrical z, and we can see a distribution along that as a function of the radius. Okay, so I think with that, I'm going to open it up for questions and answers just for a few minutes because it is now 10:26 my time, and we're going to end at 10:30. So if anybody has any questions, go ahead, and if not, I will upload this to the YouTube channel and let you know. Does anybody have any questions? As a reminder, tomorrow at 3 p.m. Central Time, which I always have to look up what time that is in UTC. 3 p.m. Central Time, which is looks like 8 p.m. UTC, so on a Friday night. I'll be going over some more advanced stuff, including hopefully some interactive volume rendering and also integration with Napari and how you can see these things. So thank you very much for being here with me. I will see you all tomorrow, maybe. Have a good one.